How many of you guys know about PDO? So PDO is Petroleum Development Oman, 60% owned by government of Oman, 30-something% owned by Shell, and about 7% owned by Total Energies and some other companies as well. So this is a very nice case study, not just from a technical standpoint, not just from a 3D printing standpoint, but how in a complex environment, abroad, we manage with different stakeholders to pull out this project off. So this presentation has already been given at ADIPEC, the largest energy conference in UAE this year, so it's a repetition of that. But the message and the reason that we are sharing this with you, we want to share the thought process and what we did to qualify a component, the 3D printed component for real oil and gas operations. So the process, I assume many of you are familiar with the FDM process. Maybe with the raise your hands, who is familiar with FDM? Fantastic, I like that, very vibrant audience. So we have a fused filament fabrication method, we have the FGF as well. We are focused on a high performance polymers. These are the polymers that potentially they have been very useful for the oil and gas environment. So PEEK is something that we have been using for decades. And given the nature of our industry in oil and gas business, and energy business, they would like the materials that they have been using and they've been performing over the years, okay? So PEEK is one of them. And that's why we focus in high performance polymers. So basically the value drivers for any 3D printing in oil and gas, again, I listed a few here: cutting cost, cutting lead time, digital inventory, maintenance, safety. I want to ask the audience, what am I missing here? I'm pretty sure you have some good downtime. Okay, fantastic. I would say downtime, I can put it on the cost, but also maybe risk, reliability. So cost, what kind of costs? What type of cost we have for, let's say, an operator like VAR Energy? We have an upfront cost and we have a life cycle cost. Okay, so if it's an international project, sustainability aspect, excellent. So maybe the way to rebrand the digital inventory could be sustainable warehousing, because sustainability is very big. Now, sustainability, the first thing that everybody thinks is environmental sustainability. That's it, okay? But also sustainability is important from a financial standpoint. So when we say sustainable, we are trying to cover all aspects of financial and environmental sustainability. So I'm going to peel it off one more layer about sustainability. So digital warehousing. How digital warehousing do you think would help you have a more sustainable operations in oil and gas? Any thoughts? So how about obsolescence, reduction of physical warehousing? Today, you don't know if this pump is going to fail and which pump is going to fail, right? So you don't know. So what you do, basically, you overstock. We talked to one of the Norwegian-based operators. They're not here, okay? I can tell you that. They said basically the obsolescence rate for the parts in their warehouse is up to 80%. This might sound not very positive, but also the way that I think we can turn this challenge to an opportunity is the size and the opportunity that we can capture. So there's a lot of improvements that we can make with additive manufacturing. So what do we, as Roboze, as a machine operator, do? So we work and engage with a lot of OEMs. And some of you, I had the conversation last night, you're from the OEM, some of you are doing reverse engineering, some of you are from the operating company. Most of the OEMs are focused for design to use additive manufacturing, NPD, new product development. Okay, about 10% of the companies that they're OEMs, they're also taking care of the components that they sold to operators in a life cycle. For example, sometimes companies like Eureka Pumps, based in Norway, they sell the pump to the operators, but also they have some maintenance services once they put the part in operations. This is very important because this slide is talking about how complex the supply chain is and what are the different stakeholders. Operators, most of the time, they really come to 3D printing because they're facing obsolescence problems. They've had a field that they've been developing, they had an OEM, the OEM is not around. That's a big problem. They want to just basically make sure that the operational excellence and integrity is preserved. They can source the part and they can basically continue the operations with less risk. So these are kind of like the stakeholders that we work with. Now, our value delivery model is basically distributed manufacturing. We do not want, Roboze does not want, I'm talking on behalf of our basically CEO and VP, we do not want to sell randomly printers to like random companies. We'll be very happy to, but our delivery model is basically to focus on locations that there are industrial challenges. For example, in Norway, where are the operations happening? We want to be, if not at, close to it as much as possible. So in that journey, we knew that if we want to just hop on this, we're going to talk to a bunch of regulatory people. So 3 years ago, we were saying, okay, we want to make this 3D printed part, and if you go to talk to a corrosion engineer or materials engineer, say, well, this is cool. What kind of specifications do you have? And we say, well, there's none. And they probably say, well, that's great. It looks good. You can be a model, but we're not going to use it. We can't accept the risk. So how do we de-risk this up to this stage? Basically, 2.5 years ago, we started a committee, American Petroleum Institute 20T, for non-metallic additive manufacturing. There were more than 50 experts on this committee that they'll have several decades of experience each. So we manage as an industry to come up with the new standards for non-metallic additive manufacturing. For your information, DNV does not have a polymer additive manufacturing standard. And this was actually a favor that they followed up with Roboze request, because we were on API and we said, really the industry does not another repeated, almost like rewarded standard. What we need is to focus on applications. And that's really what we have this presentation today. And then after the international organizations and the standardization, we started focusing on the large oil and gas players, the OEMs. We said, okay, if you really want to do business with oil and gas, they need to certify your materials. They need to have those specifications. So what we did, as an example on this slide, we're showing, we went to Schlumberger, right now they're named SLB recently, and they have a specification on our materials and also technology. So we have been basically delivering multiple parts to Schlumberger, a company that has operations in more than 100 countries, and they've been in the business, and we could meet the criteria and qualification that they need. These are big wins, all of them. This is an industry win, this is a technology win, this technology is satisfying the one big OEM, symbolic OEM. And then the largest win was that basically all the stakeholders, this was a win for all of our industry, all the players that really they contributed. And I couldn't put all the logos here, but there are like a lot more people that they actually contributed to API. So what are the methods that are approved by additive manufacturing per API 20T? FFF, fused filament fabrication. Argo 500 has this technology. FGF, fused granulate fabrication. Argo 1000 has this technology. And selective laser sintering and multi-jet fusion. Roboze does not work on this, but we don't want to make this we want to make this a very comprehensive, holistic standard so that everybody can basically make parts, and then they get their parts de-risked. So again, some of the samples and basics of the system. I'm pretty sure you're familiar with this. So let's say tomorrow you're going to pick this part and start saying that I want to qualify this component. What are the steps? How can I say, what do I need to do? Okay, first you have the CAD file, obviously. How many of you have faced challenges with getting a CAD file from the OEM? With raise of hands. Okay, one in the back, or two only? That's a very successful crowd. But anyway, so basically we hear that in the US, that's one of the challenges. They can't get the CAD file. They talk to, for example, I hope I'm going to record a line, but they talk to a pump OEM, and the pump OEM says, this is a SQ111. And another operator asks the same pump OEM about the same part, same materials, everything's the same. They say this SQ is like 222. And so the operators are confused. They say, this is the same part. Why do you name it? Oh, it was different. It was a different part. So there's a whole confusion. And this is not an additive manufacturing challenge. It's more of a supply chain procurement challenge. And everything is somehow now on the shoulders of additive manufacturing and trying to figuring this out. So the first step for identifying and understanding what you need to do and to what level of qualifications you need to perform is actually the risk level. So API's guidance, and also DNV has the same logic. They look into the criticality level of what is this part going to experience. If it's going to be something that we're going to go to a very high level risk, high criticality, basically they would do more testing and more type of rigor to make sure that this part is a quality part. After the criticality level is determined, they know per API they have to do certain testing on the materials, certain testing on the components. And bear in mind, materials qualification does not mean the part qualifications and vice versa. You cannot even say, you can't say this part is qualified, but if the materials is not qualified, there is still a risk of failure. So it's a twofold thing, basically. Now, there's a lot of printers here, and all of them, our printers look blue. There are some white ones, pink ones, some of them, there are different colors, right? So you as the end user, you're trying to figure out, how can I rely on these boxes? They're saying they can make stuff for me. All of them, they're pretty big. Some of them are even larger, like some of them are robots, right? How can I make sure as an end user that what they're building for me is compliant? So we did this exercise with Baker Hughes 2 years ago, and this was a great learning curve. They asked us to print large towers within a build chamber and extract tensile coupons from different sections of these towers, bottom, middle, and top. And then basically do tensile tests and show that if you make a part in middle or any corners of this build chamber at any height, it has a consistent property. This is very important because people think, well, this is pretty much a chamber. I can build it whatever I want. No, not true. The way that we achieve this is because the way that our system is built, we guarantee the same thermal gradient across the height. So the thermal gradient would impact the level of crystallinity of the polymers, and level of crystallinity of the polymer would dictate the mechanical properties. If you want to have a large part with consistent properties, you need to have this type of build process qualifications. Now, after the build process qualifications, you have certain coupons and certain components that you need to basically, this is guidance of API. You look into the, DSC, you can do mechanical properties, hardness. These are all classical tests that are required per API, depending on the risk level. So we do this type of testing. Then operators, VAR Energy or Equinor could come to us and say, hey, I need some of these parameters to be reported to me. I want to know if there is a 3D parts partner or manufacturing partner of Roboze making these parts in Hammerfest or in south of Norway or in eastern Norway, how do I know that you'll be able to repeat these parts again? So to circumvent that, there are some parameters and traceability that API's guidance is there. Once we do that, basically like a classical manufacturing, for those of you guys that have been around, we have MPS, we have an NCR. Any non-conformance that happens needs to be reported to the end user. There's going to be a report of that. And then we also have machine data. So today in our industry, in the oil and gas business, if you want to make sure on the reliability of some components that are made in some, let's say, Far East, you would send a quality inspector to that location and you ask that guy to watch the process, okay? Roboze machines, they're making the machine data available to you for every second of manufacturing. So this digital transformation is enabling you more traceability. There's no cheating around it. If the qualifications of this pump, this fan blade has been done and it was successfully deployed in the field, you have a digital DNA of this part. You can go back 5 years from now, God forbid, if this happened, there's a RCA, we want to do RCA, tap-wise, 5-wise, taproot, 5-wise, whatever method you want to use, you can go back and say how this part was made at this location. What was the temperature of the chamber? What was the temperature of the extruder? Because these are the parameters that would impact the crystallinity and hence the mechanical properties. So as materials engineers, it gives you lots of traceability power. So once we do that, of course, depending on the number of the quantity of our parts, there's a sampling recommendations and then also making the component itself. Now, let's go to the case study, because now after this procedure, I can share you the story that this story is not just the story of PDO. I'm pretty sure a lot of operators, also service companies, they're going through a similar story. And the story is a story of having difficulty with sourcing. I mean, we had a discussion last night about how can you source stuff, in a Hammerfest, or like when there's like a strong winter, or if you're in the middle of the ocean, like the example of Aker BP Scarf FPSO, right, one of our printers are right now. What are you gonna do? If you're on a shift on a FPSO and you're waiting for your parts and suddenly your pump is shut down, your only way is to stop. Because in our business, in oil and gas business, what do? Stop work. If there's a safety, stop work. That's it. Because we don't want to risk it. Now we have to wait for the chopper to bring the part. We have some limited spare parts on the FPSO, but you cannot keep everything. So there is a space issue. So basically PDO had the same challenge. They were using fan blades, 17 megawatts. These are very long fan blades for cooling operations in Oman. And because of the very rigorous sandy desert of Oman, they were basically abrading the fan blades. And after a while, they were actually stopped working. So the challenge was actually not technical first. They bought the whole package from a service company. They went to the service company and said, hey, we need this component of your system is breaking down. Can you fix this for us? They said, well, it's not actually our part. We have another company that we bought this from and we assembled it. So think about the complexity of supply chain. Sometimes the sellers of systems, they're also sourcing from different parts. So the operator was kind of like really cornered. They said, what do? We cannot get this part. We need this part. Our operation is shut down. Let's try 3D printing. So this is where we Shell and PDO team, they basically got in touch with us more than a year ago. We start qualifying, and as we speak, API is being written. So API was kind of foundational for this project. So this is the original materials of the fan blades. They were polymer. The materials engineers, again, if you ask any, I think, materials engineering group within any operators today, I can guarantee you 90% they have a metallic expertise. 10% maybe non-metallic. Sometimes there's not one non-metallic expert for the whole company. So this is like a reality. So in our industry, knowledge on composites is not as much as aerospace. We are heavily carbon steel driven, let's put it this way. And sometimes super duplex for offshore. So this is causing a challenge because it's robbing the opportunity from us to think about opportunities on composite and advanced materials that they can perform, and they be a corrosion resistant materials that actually can translate to value. Now, after the polymer failures, the original, they said, let's make it out of metal because that's stronger. Okay, that's just the first feeling that maybe all of us could have. It's abrading, this is breaking down, I'm taking it off. You know what? I'm going to make it out of metal. I think it's stronger. So they casted it out of aluminum. Okay, they put it in the operation. So any rotating equipment, basically, if you have to spin it, you have to basically exert energy, right? Their utility costs went up. And because of the weight of the metal, they had difficulty balancing the whole thing. So they were kind of like frustrated, and it's a very frustrating challenge. It's an engineering challenge that's combined with supply chain. So then they asked Roboze and say, can we 3D print this? This was the first question for us. Okay, let's just look at it. The first question we always ask is, who is the OEM? We always make sure the IP is okay. And Shell told us that they already have a permission from Eltafans, which was the OEM. They're okay with manufacturing these parts. And for limited numbers, they don't care. So basically, we got this in writing from Shell. Shell provided that to us in PDO, and then we proceeded. We asked them for a CAD file. They provided a CAD file. Shell, they scanned it. They didn't get this from Eltafans. They could barely even find it. This is, again, the real problems. And then we manufactured. We manufactured the first component. We look into the material properties. And this is interesting for you. So they reverse engineer the base properties of the first polymer blade. They look into the tensile, all this strength, density, and they said, this is what I have as a baseline, okay? Now, this is what Roboze claims in their materials data sheets, okay? What is our minimum criteria? So 3D printing materials, the original materials, where do we have to draw the line, failure line? Because we can't print, and we want to make sure it's consistent printing. So we set our minimum criteria as the original fan criteria. This was some agreement with Shell. And then once we start manufacturing the components, we actually intentionally 3D printed a thicker blade to be able to extract some tensile coupons from this blade, to then basically break these tensile coupons and verify the material properties. That whatever the component that we're making is having a consistent property. Now, luckily this geometry kind of allowed us. If you're making a pumping pellet, it might be a little more challenging. If it doesn't allow you to basically take the coupons, one way that you can actually satisfy the requirement is to do FAT, some testing, okay, before you deploy. So we got the coupons. Sorry, I just flipped my slide, I think. We got the coupons. We tested them on a worst case scenario, on a Z strength, on X and Y, and all of them. And then we saw that, okay, the properties are higher than the minimum criteria with some buffer. We said it's good. Then there was another challenge. So how do we machine a 3D printed parts? We have a machining expert in the back. He was telling me last night that he has more than a decade of experience on this. But none of this are in a 3D printing part, right? This is another thing. How do we machine a 3D printed parts? This was another learning curve that we brought and we learned and we wanted to share here. So we had to basically custom manufacture tooling that can hold this blade so we can basically machine this hub. Luckily today, because we have a soluble support, we don't need to go through this route. But imagine, because of the availability of fan blades and 3D printing, we can even make custom tooling for machining to enable complex machining. This is another way. So we made the part. After we made the part, we use our materials, of course, carbon PA propylamide 6. And this is the jig, one side. This is a male and a female. We manufactured it. We looked into all the properties. We did the sampling process. And then before deploying to the field, what we did, we basically balanced it. So this is a certificate of balancing of a 3D printed blade that is just about to be deployed to the field. We checked the balancing, and the balancing was satisfactory. Before we go to the field, we always do FAT. So now this is on its way to field. Now there's other challenges that field deployment of 3D printed parts. How do we create awareness for the machines? How do we do MOC for this for the maintenance team? These are all other aspects. So for the sake of the time, I would like to skip it. But what I would like to do is basically open it up to questions. If there is questions, if you think like, what can we recreate together in Norway? Because we are now developing an ecosystem very with a very good energy and momentum. Absolutely. And we will share with you data sheets for materials-based properties. So you can think about different operations. So this part also is a fan cooler that we printed this for PDO. This has been also in operations already with no problem. So one question that I'm always getting asked is, what can we print? Hey, you guys are saying that you have the nicest machine. They're blue and Italian design. Honestly, looks great. What can I print? So Roboze recommendation is that start slow, start small. Start from where we have some already case studies and validations. For example, for a swing check valve, we have done a project with an American operator in Canada where we deployed this part, and this has been in the field for more than a year. Okay, and this is still growing. The original lifetime of this component out of carbon steel was every 3 months. They had to actually take it out and then basically test it. Now, with the 3D printed part, so far it's been 18 months that it's been in operations and it's performing. There's nothing favorable of, let's say, Roboze versus others. It's all about materials. And I think you asked the right question, Trina. Is this a corrosion-resistant materials? Can this withstand the higher temperatures? So these are the good questions that we can ask and verify the material properties versus the operating environment. This is the base case scenario. And after that, we will basically take this to a next level to field test it and other things. So that's about the PDO. Hopefully this was a new perspective for you, or at least maybe you've heard about, of course, metallic application, but this is one of the very few non-metallic applications that made it to the field.